So up to this point, we've done applications of integrals that were largely geometric. And there are a ton of applications of integration. We're only going to cover a few here. You will see more of them in your career, whether you go on to further into mathematics, you go into physics or biology or chemistry or engineering. You'll see these across the board. And you've probably already seen some of them in those classes that you're taking. So the last one I want to talk about is work. And this is a more science-based application than the geometric ones we've done so far. And so the idea is this. All physical tasks, from running up a hill to turning on a computer, require a certain amount of energy to be expended. Okay? When force is applied to an object to move it, the energy expended is called work. Okay? So when a constant force F is applied to move an object a distance d in the direction of the force, and the key here is that this d has got to be a linear distance, the work W is defined by force times distance. So we get this formula. The problem with this formula is that it's very, very basic. So there's a lot of things that have to go right for us to be able to use this. First off, key wording here, constant force. So here's some people pushing a rock. They have to be pushing on that rock with a constant force. You have to be pushing with the same force at all times, which right away you realize is not going to be possible. You know, when you're pushing a rock, you're going to slowly get it going, and hopefully you're going to push it harder, and then maybe a little bit harder until you can get it moving. So that's not really a constant force, but let's just assume they're pushing at it on a constant force, which you have to do lots of times to simplify things. And let's assume that they're moving on a linear distance, okay? So a straight distance from A to B. So we can calculate that distance. So that's probably not going to happen either. A lot of times when you push a rock, it's going to wiggle back and forth because it's not perfectly round. But let's just assume constant force, linear, straight distance. If we were to calculate the work that they put in to push that rock, which is essentially the energy expended to push that rock, we could do it by knowing what that constant force was and what distance they traveled. Okay. But again, that's too perfect, right? None of those things are probably realistic in terms of the real world. Let's talk a little bit more about force first before we get into, maybe a little bit more realistic situation. So the international standard unit for force, you should know, or if you don't, is newtons. So we use N, okay? And it's defined by 1 kilogram meter per second squared. Okay, that's your standard measurement of a newton. Energy and work are both measured in joules. Okay, so if we are measuring work, which we will, the unit of measurement in the end should be joules, and it's equal to 1 newton meter. And in the British system and American system, we should really probably say too, is the unit force is a pound, okay? And both energy and work are measured in foot-pounds, okay? I prefer to do the metric system. I think, we're better off being in the metric system, but unfortunately in the United States, we would use foot-pounds. And another unit we could use would be calories. Everyone's heard that for energy. And 1 foot-pound is approximately 0.738 joules, or 3.088 calories. So when we're measuring work, we could do it in joules or foot-pounds or calories. I think we'll stick to joules. If we try and make this a little more realistic, let's just say we're moving with a variable force. So go back to the rock problem, those people pushing the rock. Let's say they're not pushing on the rock with a constant force, but pushing on the rock with a variable force. So that force is going to be stronger and lighter at certain points of times over the course of them pushing. So it would be measured by a function. But still think that they're moving from A to B, though, like in a linear pattern. So it still has to be linear motion, keep that simple, but the force could be variable. Well, the way we could calculate the work done by force is exactly with this integral right here. So this integral of the force from A to B of the force dx is a very easy way for us to calculate the work done with a variable force, but still in a linear motion. And we start at A and we go to B. So if we knew what the variable force was that those people were pushing that rock with, if we knew what that was, and we knew where they started and where they ended in terms of straight interval from A to B, we could plug that force in here. We could integrate it with respect to x and evaluate it between A and B, and that would give us the work done in that problem. Some typical problems where it's easy to calculate the force as a function would be spring problems. Okay? And Hooke's law is a good example of how we could calculate force of a spring. A couple other common problems where we could use Newton's law of universal gravitation, use Coulomb's law, which is the force between charges, but we'll do an example of Hooke's law. So Hooke's law refers to the force is required to compress, I should say, and stretch a spring a certain distance. And a nice reason why I like the spring example is because it's definitely a linear motion. So it's moving along this line. Okay? And the way you can do it is with this formula here, F equals K times D, where K is what we call the spring constant. And the spring constant depends on the nature of the spring. How tightly is it wound? What material is it made of? And D is the distance that we would be traveling. A lot of times we'll use dx for D because x would be the distance we're going to travel, and we're going to say it's along the x-axis. So if we're going from, 0 to 2, that's the distance over this x-axis. So lots of times we'll use x there for D. So we could say Hooke's law is F equals K times X. Okay? So here's an example of a spring that's sitting in a position where it's not doing anything. This is its optimal state. And then we could stretch the spring out by placing a weight on it, a certain distance x, and we can put another weight on it, stretch it out another distance x, etc. So this is the concept of Hooke's law. Now here's a very basic example of a Hooke's law work problem. So assuming we have a spring constant, so sometimes you'll calculate this, but let's just say we have our spring constant given to us of this 400 Newton meters. Okay, find the work required to first stretch the spring 10 centimeters beyond equilibrium. Now, we have a couple of things here. We're stretching the spring, so it's directional, right? So if you think about a spring sitting at 0, okay, that's its equilibrium, and we're going to stretch it 10 centimeters. Well, the spring constant is given to us in meters, so we really should probably take this 10 centimeters and write it in terms of meters. So maybe this is 10 centimeters, but in terms of meters, it would be 0.1 meters. That way our units of measurement all line up. So we want to go from 0 meters to 0.1 meters. So in order to do that and calculate the force, we would have to do the integral from 0 to 0.1 of the force. Well, we have this formula that says the force can be equal to K times, in this case, X. We don't know, the distance is moving, right? So since distance is moving along, say, the x-axis, let's just call that x. And the spring constant was given to us as 400, so this would be 400x. So if I took this 400x dx and I integrated it between 0 and 1, that should give me the work done. And so that's a pretty easy integral to do. We would get 400x squared over 2. We between 0 and 0.1. So we would get, what, 200 times 0.1 squared, which would be 0.01. So we would get 2 joules. All right, so now what we want to do is we want to look at this other one. This one says we want to compress the spring. So you have the spring sitting here in equilibrium, right? We want to, instead of stretching it out, we want to push it in. Now, it's compressed 2 centimeters more when it was already compressed to 3 centimeters. So if you think about that, just, here's equilibrium. It was already compressed to 3 centimeters. In terms of meters, 0.03. Remember, I want to convert everything to meters, so this will be 0.03. It was compressed to 0.03 already, so that's where it's sitting. And then it went 2 more centimeters, which would be another 0.02 meters. So now it's at 0.05. So the spring is going from 0.03 to 0.05. Okay? So then we want to figure out what the work would take to go that far. And, sorry, these are on the negative side. We should remember, we're compressing, we're on the negative side of 0. So if we go to set up our integral, let's get rid of some of this. We already know that we're going to use the 400x. So we're going to go from negative 0.03 to negative 0.5 dx. So we already know we're going to have this 200x squared. We have to plug in negative 0.03 and negative 0.05. So we're going to get 200 times 0.05 squared minus 0.03 squared. So we'd actually have to do that computation. Pretty simple. We got rid of the negatives because we're squaring them. So 0.05 squared would be what? 0.0025 minus 0.03 squared would be 0.0009. So we would get, what, 200 times, what will we get if we subtract those? We would get 0.0016. And then 200 times that, so we would be 2 times 0.16, so that would be 0.32. So 0.32 joules would be the amount of work we would have to put in to compress this spring, the amount it asked. And so again, you can see that integrals can be used for a lot of things. Like I said, this is just touching the surface. You will come across a lot more examples of applications of integrals along the way.